is equals to the minimum ST cut. So this was done, right? So you saw this particular statement.
Yes, sir.
Okay. Now, so how was this one done? I want you guys to kind of tell me how was it was done. So was the flow created? If I give you a, just 1 second. Hello. So class session is it? ठीक है good afternoon. No. No. Okay, good. So I think the other class got over. So hopefully we will join us. So how was this proof of maximum min cut done? So was it done by saying that, okay, so here is a graph with a minimum cut of something, and then you can slowly create a flow of that much amount? Hello?
Yes, sir. Yes, that was.
Okay, good. That is how it was done, right? So the basic proof that is there, right, is that you start with a graph, G with mean cut, say C, okay, and then you slowly increase the flow, the ST flow, until you reach until the flow is of capacity of size C, right? So every time you kind of say that, okay, so if I have not reached C, that means I have still left with some amount of min cut, and you start with one particular path from S to T, either through the graph or through the graph along with the reverse edges, okay, right? And then try to pass a flow from that direction, 1 unit of flow, or not 1 unit of flow, the maximum unit of flow that you can send. Am I right? Is this what was done?
Yes, sir. Yes.
Okay. So if this was done, then one important part of this proof, I don't know whether it was pointed it out to you, was that, okay, an important fact. And this is something that you guys should check or verify with your proof, that if the capacity of all the edges is a positive number, okay, is a natural number, so not R, but natural numbers, okay, integers, okay, then there exists what we call as a integer flow, integer ST flow of maximum of min cut, volume. Or in other words, what's the integer flow? What is an integer ST flow? An integer ST flow is a flow where along every edge the flow is a integer value. Okay. And now, how is this one true? This actually follows from the proof here. Because what happens is that every time as you start with a graph, and now note that this graph now has a integer capacity, integer capacity, so which means the mean cut is an integer, right? And therefore, what you can do is that every time when you augment this, when you increase the flow, you start with you find out a path, right, along which you can send some unit of flow, but the minimum unit is an integer again. So you'll increase, this increase always happens by a unit amount, by an integer amount. So you will end up getting a flow which is a integer flow. Is this clear?
Yes, sir.
Okay. Was this one was pointed it out to you in the class? Hello?
No.
No. Okay. But I would like you guys to go and think about it. Okay. This should be, you should be able to verify this particular thing. Okay. It's really proof of it. But once you have this particular fact, then Menger's theorem would follow very easily. Okay. Why? So let's see here. Okay. I have a graph. Okay. Say S and T. Okay. Now the mean cut, then the mean cut is C. Now see, this graph has all the capacities are 1, right? All the capacities are 1. Okay, unit. So there is a mean cut is C, meaning there is a cut of size at most C. Right? They can be have a multiple cuts like this, and you can have some edges, back edges, many of them back edges. I don't know how many back edges are there. Note that back edges don't count to the cut, right? Only the forward edges counts to the cut, right? So what do I have? I have that the mean cut is C. So mean cut is C means that in this ST cut there exists a ST integer flow of size C. So this is because of the max flow mean cut theorem. This implies that there exists an ST cut. Okay, good. So consider that flow. There is some flow. I don't know what is that flow. Some kind of flow is there. Note that this is an integer flow, right? So that means in every age, only an integer amount is passing. The capacity of every age is just 1. What does it mean? That means either you are passing 1 unit along an edge or 0 unit. Okay. Fine. Now, once you are done with that, then what I do is that I just find a path along the flow, just a flow. So flow is a particular set of edges that are there. I find one path along this flow, meaning a set of a path from S to T where the flow is 1. Okay, the flow is 1 in each of them. Fine. So this is a path P. Okay, I can find a path P. So I have this graph G. Now from this path, I construct. So what was G? G had a mean cut was C, max flow was how much? C also. So from G, I construct say G minus the path P. I remove that path. I'm not going to use that path. What is this? So this one, how much does it have? Let's see. What do you think is the max flow here? What do you think is the max flow?
C minus 1.
This is C minus 1. Actually, max flow is bigger than C minus 1 because I have just removed one unit, right? And actually mean cut, since I have removed one edge, so mean cut is less than C minus 1. And since max flow is equals to mean cut, so I have the max flow is exactly C minus 1. So that means I have got this new graph G prime, which has mean cut equals to C minus 1. So if I do an induction kind of stuff now, let's think of it. In this case, what do I have? That in this graph, if I use a different color, there are C minus 1 edge disjoint path from S to T. So say if I can use induction and I can prove here that if G prime has C minus 1 edge disjoint path from S to T, then in G I have all those paths plus this P which was removed already, which is another edge path that is disjoint from all the previous paths, right? So by induction, I am not going to details of writing the induction, but you can see why it is happening. If you cannot, just let me know that by induction from here, we know that G has C edge disjoint ST paths. And this is the Menger's theorem. Is this clear? Is this clearer than what it was earlier? Hello?
Yes, sir. Yes, sir.
Okay. So actually, the way in which this max flow mean cut theorem, this is a very powerful theorem, by the way, very, very, very powerful theorem. Okay, and we will see another very nice application of this max flow mean cut theorem. If you have managed to follow whatever I just now did here, then you should be able to follow the other theorem also, and that is exactly what I am going to do now. But maybe just let me wait for a couple of minutes. Please let me know, did you follow whatever has been done? Any questions? Hello? Okay. I'm assuming that no answer means that you have understood everything. Okay. Now, let me go into the other thing of matching. Before I start with matching, let's start with the bipartite graph. Okay. What is a bipartite graph? Do you guys remember what a bipartite graph is?
You say it can be divided into two sets that two set of vertices that don't contain any edges between them.
Perfect. So this G basically is a set of vertices and set of edges in which I can write that the vertexes can be written as the disjoint union of the left and right, and the edge is nothing but only going from left to right. And this is just a disjoint. It's a you can think of it as a undirected graph, right? So this is a bipartite graph. Do you have some other property of a bipartite graph? Maybe I can ask somebody else. Monideep, are you there?
Yes, sir.
Yeah. Do you know of any other property of bipartite graphs?
So it doesn't have a cycle. I mean, not an odd-length cycle.
Very good. Okay, so this is something that was given in your, I think, in problems set to try out, that G is bipartite if and only if G has no odd cycles. Okay, excellent. So you guys really know what a bipartite graph is. Now, can somebody say now what is the matching? Mayank Tiora, are you there?
Yes, sir.
Yeah. Can you say what a matching is?
Sir, I knew, but I don't. I cannot recall it.
You knew, but you cannot recall it.
Yes, sir. Matching is related to vertices, vertex set, but I cannot recall it.
Okay. Supriya Mondal, are you there?
Yes, sir.
Yeah. Do you know what a matching is?
Yes, number of non-adjacent edges.
Okay, good. So if I give you a graph G and set of edges, a matching is nothing but a subset of edges such that, I mean, no two edges are adjacent. Okay, or in other case, if UV is in matching M, then VW is not in M. Okay, so maybe let's think of it in a bit of a picture wise. So I will think of it in the bipartite graph setting, or maybe I will not think of it from the bipartite graph setting, sorry. Let me think of it in a general graph setting. Okay. Say I have this graph. A matching is basically, I can say, okay, this one, and this one is a matching. Okay. Why? See, no two edge, okay, is adjacent, meaning they don't have a common vertex point. Note that if I had not taken one particular matching, so for example, just these two red ones, they would have also given me a matching. Okay, a subset of a matching is a matching. Okay. Now there can be many matchings, by the way. This is matching. Maybe I could have taken this one and this one. That could have been a matching also. Right? Or now there is another concept of perfect matching. Now, what is a perfect matching? So let's think of it in this way. Okay, that you come to ISI, say, and you want to so you have this hostel rooms that you want to take, right? And every student kind of gives a list of students with whom he or she wants to or are willing to share the room. It's all the rooms, hostel rooms are shared rooms. So you have to share it with someone. And every student gives a list of rooms that he or she wants to share. Right? Now a matching is basically saying what? Okay, this person A goes with person B. Person C goes to person D, and so on and so forth. It's a matching. I match this person with that person basically means that I will say that this two person in a one matching goes to a shares a particular room. Not that, of course, if person A and person B share a room, person A and person C doesn't need to share a room because A has got a room, right? So an allotment of the rooms is a matching. But another thing that is required for a good property of a matching should have is that every person should be given a room, right? So every person should be given a room, and let's say ISI has this weird rule that one room has to be shared. Okay, if something is not shared, then it is not possible. Okay, so a perfect matching is M is a perfect matching. So I have given a graph G, and a perfect matching, M is a perfect matching if, first of all, first property, M is a matching, and to every vertex is matched. Or in other words, every vertex has a corresponding vertex with which that edge is in the matching. Okay. Now, what do you think here in this graph? Does this graph have a perfect matching?
No, sir.
No. Why not?
One
Why not?
vertex towards the bottom, there is one vertex from which
This
that
is-
curve ends.
There is
So
a
this is
odd
not a
number.
perfect matching. This particular matching is not a perfect matching. That I agree, because this vertex doesn't have a match thing. But does it mean that it doesn't have a perfect matching? Maybe I can do something clever, like I can assign this one or something like that. Maybe some other matching will give you a perfect matching. So does this graph have the perfect matching?
There's odd number of vertices, so it can't be.
Wonderful. It has odd number of vertices, so it cannot be. Right? Good. Very good. So let me let me try to do something more tricky then. Okay. So first of all, let's say so one property, right? I can think of it that if size of the vertex set is odd, G does not have a perfect match. This is like kind of easy because every vertex has to be matched to something else, so it must be everything must happen in pairs. But does it mean that? So does it mean that? So to any graph with even number of edges, number of vertices, has a perfect matching?
No.
No. How many of you think it is no, and how many of you think it is yes?
Sir, do we have to choose from the existing edges, or we can
Yes,
assume?
you have to choose from the existing edges only. You have to choose only from the existing edges. I mean, edges that are there in the graph. Awanish Kumar, are you there?
Yes, sir.
Yeah. Do you think if any graph with all even edges have a perfect matching?
No, sir, it's not necessary.
It's not necessary. Can you give an example?
Sir, if a vertex is disconnected from all other vertex, then there can be a graph. It can be, it can
Oh,
be
very nice. So this is a good
removed from it,
example.
and it will become an odd number of vertices.
Yeah, okay, good. So it says that, okay, what happens if the graph has a, so like here, if I just put a vertex here, it's an even number of vertices, but basically it's odd because it is not connected. This vertex is not connected to anywhere else, and so it's not possible. Very good, excellent. In fact, this is also not possible even for connected graphs. For example, let's think of this graph, okay? So note that this graph has 6 edges, right? 6 vertices, and it doesn't have a perfect matching. Say I take this vertex as this edge as one of the matched edges. That means this vertex gets matched, this vertex gets matched, but then the remaining set of vertices are not matched or cannot be matched. Okay. So there are lots of these graphs for which there cannot be a perfect match. So the question that we want to know is that what kind of graphs, or maybe I should not write it what kind of graphs, but what property of graphs ensures there exists a perfect match. So this is the question that we want to ask. So I have this graph here, okay, and I'm just looking at bipartite graphs, okay, and I will just, and for whatever I'm going to do now, I will just talk about bipartite graphs. For the case of non-bipartite graphs, something similar can be done, but it's much more complicated. Let's put it this way. Okay. Say I have this graph here. Do you think such a graph has a perfect matching? Or when do you think a graph has a perfect matching? Can this graph have a perfect matching? Say. Can you give me some properties of this graph having a perfect matching? So this is the L side, this is the R side of the bipartite graph.
Equal number of vertices should be there in L side and R side.
Very good. So first property that should be there is that size of L must be equal to size of R. It is something exactly similar about, this is a bipartite thing, right? So it is like say you have n jobs, positions, and n people, right? If you want to ensure that every job has a person and every person has a job, then you should have these two numbers to be same, right? And so similarly here, L must be equal to R. That's first position. So okay, what happens if I add some stuffs over here? So maybe I will just redraw stuff here. Just 1 second. Yeah, so the 5 in each thing. Okay. Does this graph has a bipartite graph? Does this graph has a matching, perfect matching?
No, sir.
No. Can you say why?
The top vertex in R side is matched with both.
Very
two.
good point. See, both these vertices are matched to this. And they kind of looks like a disconnected part almost, right? In fact, they are disconnected, right? So, okay, maybe it is not disconnected. Maybe let me add an edge. In that case, what happens?
So degree of node should be even.
Degree of node should be even. Why? Why?
I think in that case we can have perfect matching.
If you have degree of node to be even. No, that's not necessary. Let me just give you an example. Okay. Maybe I will give you an example. Okay. 1, 2, 3. Oh yeah, I need some very bigger picture of that. One second. Yeah, so something like this. Note that this graph has every vertices have degree even. But I claim that neither does this graph nor does this graph has a perfect matching. Can you say why? First of all, let's think out here. Already you kind of told that when this edge was not there, then you told that this graph does not have a perfect matching. Can you say why I claim that this graph also doesn't have a perfect matching, even after I add that particular edge? Why?
So maybe because in the left side there are two vertices at the top, which are connected to the only the top vertex of the right side. Now,
Exactly. Very good point. So look at these two vertices again. Like these two people want this vertex, right? So think of it this way, that there are some set of toys and there are some sort of kids. Okay, so these two kid now say that I want this toy, that's all. I don't care what happens. That is all that I want. Now, this toy, maybe somebody else also wants it. But 2% is saying that I have to be given this toy. And this is not possible, right? One toy cannot be given to two people. So it would be impossible to satisfy both of them. So in this graph, we will not be able to satisfy both of these things in a person. So this graph does not have a perfect match. Now what happens here? Can you see what happens here? Let me give you a hint. Something very similar here happens. But here the number of kids is this 3 kids. See, these 3 kids are saying that what I do, what I want, all these 3 kids are saying that either you give me this or this. So there are 2 toys that these 3 kids want to share. Or these 3 kids says that, okay, I want either of these 2 toys. And that is again not possible, right? how can you give 2 toys to 3 kids, satisfying them? So it's not possible. Is it clear that these 2 graphs does not have a perfect matching?
Yes, sir.
Okay. Now, whatever I just told, can you write it in a, or tell me in a mathematical form? What does this statement mean? Except for talking about in kids and toys, what is it that's happening? Let's see. So here there exists a subset U of L, and I am looking at the things that these 3 kids want. What does these 3 kids want? These 2. What are these 2? These 2 are nothing but neighborhood of U, right? So what this problem this happened was that, okay, there exists a U subset of L such that the neighborhood of U, the size is strictly smaller than size of U, right? And when such a thing is happening, it is like these 3 kids wanting 2 toys. Okay, and then what do? You cannot have it, right? So perfect matching exists implies that there cannot be any such U. Is this clear? Or should I repeat it?
It's clear, sir.
It's clear? Okay, good. Okay, so I have got 2 properties, and particularly if you think of it, this property is a special case of this property, okay? This is a special case of this property and says that, okay, a perfect matching exists if that implies that there does not exist any subset of U, L, such that the neighborhood of U is strictly less than size of U. Now, the beautiful part of it is that this theorem is an if and only if theorem. And this is what is called the Hall's marriage theorem. Now, why is it called Hall discovered it, and why is it called a marriage theorem? I guess I don't have to explain it to you guys. But the more interesting thing is that why is this statement, why is the opposite true? And that is not very trivial. So in other words, I'm saying that, okay, if there doesn't exist any such U such that the neighborhood of U shrinks, okay, I can call this particular expression as neighborhood of U shrinks. So neighborhood of U is less than the size of U. In that case, we can say that the perfect matching exists. Okay. I don't have to prove this direction, right? This direction seems to be easy. This is obvious to see in some sense. This direction is not at all trivial. Maybe I'll give you a couple of minutes to just think about it. How can you approach this particular problem? If I ask you to solve it, how can you try to solve it? If you have any suggestions, you can unmute yourself and shout out your ideas, suggestions.
Sir, can it be done in this way? Like we take the whole graph and we don't have any. I mean, we have one part and yeah, another part, and we don't have any. We don't have any such condition like neighborhood of u is less than neighbor of a
Sure.
size of u.
Yeah.
So we can take one vertex from L and one vertex from R, and such that two have a edge between them, and then separate it from the rest of the graph, and take the rest of the graph, and again we apply the same condition, and thus we can take out one by one all the vertices.
Okay, you can try to prove it. Okay, now there is a proof of this kind of stuff, but it is much more complicated than how you are stating it. Things will become very ugly very soon. Okay, because it's not necessarily that, so it's not very easy to see that what is the thing that you need to, I mean, how to do this kind of recursive thing or inductive stuff here. Okay, but there is a proof using like this kind of technique. Okay, so what I'm going to do is something that if you look at any graph theory book, you will find this Hall's-Marriage theorem, but it will be written as a separate proof, and you will see it here. But here, what I will going to do is that I am going to use the Max-Flow-Minkowski theorem to prove it. Okay, so I will prove by contradictions. Okay, so I will prove by contradiction. So what does it mean by that? I will say that, okay, let G be such that for all U subset of L, neighborhood of U is greater than or equal to size of L. Okay, and let, okay, so I should not call it let, so G is this property, and let G does not have a perfect match. I will find a contradiction from here. Okay, good, fine. Now, before I go, as I told you that I will use, so just remember this thing. This is what I'm going to prove, okay? This is exactly what I'm going to prove. And I've already told you that I will be using Max-Flow-Minkowski theorem somehow. But I have to set up the Max-Flow-Minkowski theorem. I have to set up a flow. What is, so I have this graph, right? And I have some set of edges over here. What I will do is that I will add a vertex S over here and a vertex T over here. And I will draw an edge to all these L things. Okay? And an edge to all these R things. Okay? And I will add some capacities. Okay, I have to find out directions. The directions will be always from the left to right. I am directing all the edges from left to right. Okay. And what are the capacities that I give? I give capacity 1 to all these edges. I give capacity 1 to all these edges. And I give capacity infinity to all these edges. So I started with this graph. So this one was my graph. And I added this auxiliary S and T, added directions, and added capacities. And the first claim that I have is something very simple that you can easily see, that, what is it? So if G has a perfect matching, So rather I say G has a perfect matching if and only if this new graph, let's call this one G tilde has a max flow of size of L. Right? But if it has a size of L, okay, of course I'm assuming that the size of R equals size of L and all. What happens here? That if I have a flow, if I have a max flow of size of L, then in some sense you can think of it that by Menger's theorem, I have a max. So first of all, I will have a max cut, a min cut, which means that I will manage to produce a set of size of L number of disjoint paths. And since no edge is coming back, so all the edges will be of this form, right? I mean, all the paths will be of this form. So there will be only one path used in the middle. And those set of paths better be disjoint, because what can it be that one path goes like this and the other path goes like this? No, because these are all unit paths, right? Because this is a edge disjoint path, right? So this one and this one has to be edge disjoint, right? So one direction will follow from the Menger's theorem.
Sir,
Yeah, yeah.
Sir, what is the intuition behind giving infinite capacity to the?
Yes, I will come to that.
Okay.
You'll see that why I gave this one. Okay. But I'm just, yeah. The other thing is actually that if I have a flow, right? I have some, if I have a perfect matching, then I can always pass on that perfect matching, meaning every L has a mapping to R, unique element to R, right? So I can pass on that one unit flow through that edge, right? And therefore, I can achieve a max flow of this size, right? So G has a perfect matching if and only if this one has a size L. So if you go back to this statement, that was what I wanted to prove for contradiction, I would have to prove that. So I have, what all the contradiction do I have? I have this property and I have the G does not have a perfect matching, meaning this graph has a max flow of size less than, so by contradiction, G hat has max flow of size strictly less than L, which means again that G hat has min cut of size strictly less than L. Sorry, what am I doing here? Strictly less than L. Is this clear so far? Hello.
Yes, sir.
Fine. Good. So if you have any doubts, please stop me, okay? Because there are certain set of ideas that are happening here that might be a bit confusing. So, okay, so there exists a min cut that is size less than L. Now let's start with that. So that means there is a min cut. How does the min cut happen? The min cut will take, it's a ST min cut. So it is something of this kind. Some bits of some elements in S. So S is of course in this side in one part. Some elements of L is in this on the on this part. Some element of R is in this part, and similarly some elements of L is the remaining set of elements is here. The remaining set of R is here, and T is here. So this red line that I have drawn is a generic cut you can think of. A cut will look like this, ST cut. Right? I'm not telling what will be there. Fine. Now, what is the property that is there? That the size of this cut is less than L. So let's see how many of elements are here. How many edges are here? So let's call this one K. So the K element of L is here. So that means it is going to cut how many of them? N minus K of them. Right? N minus K of these edges. And how many elements of there are there? So maybe let's call this one as R, small r number of elements are here. So this is the number of elements that are being cut. Right? So I have a K element over here, R element of here, and the cut size is of size how much? Cut is therefore this set of elements, which is N minus K plus R, right? Plus something that cuts here. I might be cutting some edges over here, right? How many edges should I be cutting here? Would I be cutting here? I'm counting the cut. What is the cut? I'm counting. Count basically the number of edges it is cutting, right? It is cutting some edges over here. It is cutting some edges over here. And then it's cutting some edges like this from the S side to the T side. How many edges is it cutting here? Let me say it. Also, we know that this is strictly less than L. By the way, the cut is strictly less than L. Right? Oh, sorry. This is not should not be N. What am I doing? Why is it N? It should also be L. What do you think? How many edges should I be cutting here? Any idea? Who was the person who was asking me about the infinity capacity?
Sir, me, Aditya.
Yeah. Can you now see why the infinity capacity is there? Okay, so let's say it cuts, let's say that it cuts an edge here, okay? Let's say that I will make maybe a bold one for here. Okay, so let's say it cuts an edge like this. This is a very bad one, but whatever. Then what will be the cut? What would be the capacity, the size of the cut? The size of the cut is all these edges have capacity 1. That's why I counted it as L minus K. All these edges has capacity 1. That was I counted it as R. But this edge has capacity how much? Infinity. So even if one edge is cut here, even if it's one edge is cut here, this will become infinity. Right?
Yes, sir. Now,
so in that case, you cannot expect this expression to have hold. Right? So this cut, any valid cut that is a less than L cut cannot cut any edge from L to R. Note that it might be able to cut some edges from maybe here to here, but that's fine. It can cut some edges from here to here, but that is not what I'm cutting. I have to look at all the edges that goes from the S side to the T side. Okay, so there exists, because of the infinite capacity, I have ensured that this capacity cannot cut this, the minimum cut cannot cut any edge from this to this. So the total contribution for this one has to be 0. There is no edge. So there doesn't exist, or for maybe I should write it here. For the minimum cut, there doesn't exist any cut edge from S side to T side. This is because of the fact that I put it as infinity. Okay. So a cut that is the minimum cut that is less than L has this kind of a count. And what do you see from here? If this happens, what does it mean? This means that the L is less than L minus K plus R. If you just do this calculation, you will get, therefore K is strictly more than R. Okay, so in that case I have got this set here, which is K. All its neighbors, see, none of the neighbors comes here, so all its neighbors must be above, so must be within R. So here is this set here. If I call this set, maybe I should use some other color. If I call this set to be my set U, the neighborhood of U is within this set, right? So I will have, if I call U to be this set, okay, then neighborhood of U is, so size of U is equals to K. Neighborhood of U is less than R, which is strictly less than K, which is equals to size of U. Okay, so in other words, if there doesn't exist, if there is a cut of size of, if the minimum cut is of size less than L, then there will be a U which shrinks. Contradiction from what the initial statement was saying. Hello, how confused are you guys now? So I mean, it is actually quite simple, okay? And I would think that you should go and think about this particular problem, okay? And it is both the Menger's theorem as well as this Max-Flow and the Hall's marriage theorem. These are the two theorems that have a very nice application of the Max-Flow mean cut theorem. And it would be something that you should follow. It is not hard. So of course this video will be uploaded. So you should go over it again. Okay. And If you want, we can go over it in another class or have a tutorial on this particular thing also. Okay. Hello.
Okay,
Any
sir.
doubt? Yeah. Sorry. Sorry, can you say whoever was saying?
No, sir, no doubt.
Okay, perfect. Excellent. Okay, so so this one was an application of Max-Flow Min-Cut theorem to matching. So in the last bit of things that I need to cover, or I will cover rather, is this concept of what is called as a planarity. Okay, and the concept of planarity is something that okay, so consider this graph. Now when I draw this graph, how many vertices are there? Hello?
Yes, sir.
How many vertices are there?
4.
4. But when I drew, the problem is that, see, there is an intersection over here. The issue is that I have not drawn it in a way that this graph these two edges are intersecting when I'm drawing. So this is not a good drawing. This is not what is called a planar drawing. Okay. This is not a planar drawing. Fine. So what is the planar drawing of this graph? It is basically this. This is the planar drawing of this graph. Note that these two pictures are the basically same graphs, but they are drawn in a different way. While this has an intersection, artificial intersection, this particular point is not a vertex, but it has a intersection. This one does not have an intersection. So this is what is called a planar drawing. So if you can draw, and this is not. So a graph G is planar if you can draw G on a paper, okay,
Without crossing edges.
yes, without any edges crossing. Okay, so that is called planar. Now you might already start thinking that, okay, is all graphs planar? Actually, it is not. I would ask you guys, so I will not be doing this particular, I will not be spending too much time on planar graphs today, but I want you guys to go back and think about this concept, and if possible, read whichever articles or books that you can get on planar graphs. Of course, I will do a class on Friday and possibly another class on Monday where we will be talking about planar graphs. But for now, I want you guys to go and think about this particular graph. Okay, and try to convince yourself that this graph is not planar. Okay, try to convince yourself that this graph is not planar. Another graph you kind of try to prove is not planar is this graph. See, this graph is what is known as the K5 graph, meaning because it's a complete graph on 5 vertices. And this graph is what is known as the K33 graph. It's a graph which is a bipartite graph on 3 on each side, and it's a complete bipartite graph because every vertices on the left hand side is connected to every vertex on the right hand side. Proves that these two graphs are not planar. Okay. I know that you guys had a long day, and I really don't want to push you too much into this day, on today's thing. I want you guys to go and understand this Max-Flow-Min-Cut theorem as much as you can, and think about this concept of planarity. Try to prove these two graphs are not planar. In the next class, we will try to see some properties of planar graphs. Okay, we will see some properties of planar graphs. And secondly, some which graphs are planar or which planar. We'll try to answer these two questions. Now, the planar graphs, I should just say once that planar graphs do appear a lot in many nice, easy applications. Because you can see that this kind of non-crossing of edges is something that is very useful, right? For example, if you are drawing if you're trying to make a circuit board, you need this kind of properties. You cannot have the wires crossing each other and so on and so forth. Similarly, if you give you a graph, right? Say I give you a graph, sorry, not graph. If I give you a map, okay, a map of the world, say, okay, a map of India, right? So say I have a map of India here, some kind of stuff like that. And then you have these various states and all those kind of partition divisions that can be there and so on and so forth. Now, if I think of every possible state as a different vertex, right? And I draw an edge between two vertices, if these two states share a common border, right? In that case, what you will get is a planar graph. So a map gives you a planar graph. Now, one important thing in the map you have seen, you have learned it in your from your time when you have started looking at maps and all, that in maps every country or every state is drawn or colored using a different color, right? In such a way that no two adjacent country or adjacent state have the same color. How does that translate to here? It translates that it's a proper coloring of the graph. You know what a proper coloring is, right? A proper coloring of a graph basically means that you color the vertices using colors, and in such a way that no two adjacent vertices have the same color. So a coloring of a map, or maybe I should write it as the proper coloring of a map, basically same as a coloring or vertex coloring of a planar graph. Now the question is that what is the minimum number of colors required to color a planar graph? Now, if you have heard of this very well-known theorem names like 5-color theorem, 4-color theorem, and so on, it is in this concept. In the next class, on Friday, we will go over planar graphs, and we will prove that the planar graphs are 5-colorable. Can be colored using 5 colors. So this is exactly what we will be doing in the next class, and I would encourage you to please go over this concept of planarity and prove that K5 and K33 are not planar. Okay. I think I will stop today. I don't want to continue for too long because I know that this was a bit of a long day for you guys, mostly because of my mistake. Yeah, so sorry about that. And yeah, so any other questions you have? If not, we can stop the class.
So that map part, can you tell once more?
Yes. So say I have a map, right? There's a map. Here is a country. Here is another country. Here is another country. Here is another country. Here is another country. And
first part, India part.
yeah, same thing. This is a map, right? So this is a state. Okay, so here is the state and all. Now every state can be represented by a vertex, right? And I can draw an edge between any two pairs of vertices if the states that they're representing are adjacent or have a common border, right? Because if I have a common border, then I can go to the border. I can take a road from here to, so you can think of them as capitals of this particular states, right? I can drive from the capital to the border, and from border I can go to the state. So by doing so, I can draw a graph, which basically, right? I will be able to draw a graph which is basically kind of give us a graph which I have a drawing on the paper. So a map can be represented as a planar graph, or I can get a planar graph from a map. Okay, and then the reason I kind of talked about it is because of the coloring, right? So if I have to color this place as yellow, then I will basically say that, oh, this vertex will be colored yellow. If I have to color this graph as green, I say, okay, that means this vertex is green, right? And by doing so, a proper coloring of this map, meaning any two adjacent pair. So I cannot color, say this one green because this one is already adjacent to it, right? A proper coloring will basically have used different colors. Maybe this is blue, right? And then maybe this is green, this is yellow. But then this vertex has to be colored, say maybe pink or something like that. So if I give you a proper coloring of a map, it is same as saying that it's the proper vertex coloring of a planar graph. Okay, so a map, the neighborhood of the graph, neighborhood of a map or a map's connectivity can be represented as a planar graph. Is this clear?
Yes, sir. And sir, if something about number of colors, it can like pi or something you said.
Yes. So okay. So there is this famous theorem called the four-color theorem. Okay, this is a very famous theorem, four-color theorem, which basically says that any planar graph can be colored with four colors. Or in other words, any map can be colored with four colors. This is the hard theorem to prove. This is one of the very hard theorems to prove. Okay, we will not be proving that. A slightly weaker version is called a five-color theorem. That any, so basically it says that any planar graph has a five coloring. I mean, a chromatic number is less than 5. This is slightly easier, and it is sometimes provable. I mean, I sometimes prove it in the class, so I don't know whether I will be able to prove this particular theorem in the class in my on Friday. But there is a 6-color theorem, so which is basically says that any planar graph can be colored with 6 colors, and this is something that I will prove. So I will certainly prove this one, and I will try to see if I can prove this statement. I am not 100% sure. This one I will not prove, but many of you who are familiar with the concept of graph theory might have heard of this particular term. That's what I'm using it. 4-color theorem. It is one of the most celebrated theorems in this field of graph theory. That any planar graphs is colored using, can be colored in 4 colors. Converted to a map, any map can be colored using just 4 colors.
Sure, but if the first one is true, then second two are kind of obvious, isn't it?
Obviously, but I will not be proving the first one. Right? First one is very complicated. So of course, this is, I mean, 4-color implies 5-color implies 6-color, obviously. But I will prove you the easier one. Okay, I mean, at this point, you can say, oh, there's a theorem, then let's move on with it. But I'm saying that I will at least give you the proof that it is 6-color. I will give you the full proof of it. And I will try to convince you that you can also color it using 5 colors. But the fact that you can prove it using 4 colors, you can only convince yourself by looking at the Wikipedia page, which also doesn't have a proof of it. But just a statement. It is fine? Any other questions, doubts? Okay, so if not, let's maybe stop today. We will meet on Friday at 2 p.m. Oh, by the way, one assignment has already been posted, and that's due is on next, I think, Wednesday. This is on graph theory. So please Yeah, remember that. Okay. Thank you.